Okay, excellent. Thanks for coming out, everyone, this morning. Thank you for the introduction, Bob. Gave my full history there. Before Emerson and Dan talk about some of the research results from 2014 and how those decisions or how those results can help some decisions in 2015, I'm just going to take a brief 10-15 minutes to introduce myself, talk about some of the work that I've been involved with in the past, as well as some work moving forward, and really just focus on the topic of soil nitrous oxide emissions and how we can relate N2O emissions to fertilizer management. This is a topic that probably many of you've heard about before, but I think there's a lot of opportunities for achieving agronomic goals that we're accustomed to while managing fertilizer in a way to reduce N2O emissions and really having no impact on the bottom line. As Bob said, I completed my PhD in postdoc in agronomy at UC Davis. I was actually working in rice cropping systems out there and focusing on soil nitrogen management and fertilizer management to reduce greenhouse gas emissions while maintaining productivity in rice cropping systems. This is just a little bit of some of the results from our work. We were looking at both N2O as well as methane emissions and monitoring that over the annual cropping cycle. Unfortunately out there, the ground is not frozen in the winter, so we're having to go out and measure these things year round. But I think that really translates into some of the work that I'm hoping to accomplish here in Illinois. A lot of my program will focus on nutrient management options and further looking at ways for increasing nutrient uses efficiency as well as minimizing losses. And I think that the broad setting, just mentioned this before, is that I'm very interested in highly efficient agriculture, and I think production agriculture does achieve some of the greatest efficiencies out there. I think we have a lot of potential for documenting those efficiencies and displaying that this is a really promising way to meet both our agronomic and environmental goals moving forward. And I would say that that's for Illinois as well as work that I'll be doing internationally. So just a primer on nitrous oxide. We're not going to focus too much on the chemistry because I don't know any of it actually, but you know, N2O is a very simple gas. It's a naturally occurring gas, 2 nitrogen atoms, 1 oxygen, very simple molecule, and it's present in Earth's nitrogen cycle. It's been around for a long time. The problem is that when N2O gas is produced in the soil and released to the atmosphere, it acts as a very potent greenhouse gas. So it's got a global warming potential around 300 times that of CO2. So very small amounts of N2O going into the atmosphere can have a very big impact. There are a number of microbial reactions in the soil that are contributing to N2O emissions. We're not going to spend a whole lot of time on this figure, but I just want to point out that we have both nitrification pathways here as well as denitrification pathways. Really the thing to notice here is the yellow boxes are N2O, so pretty much any form of available or reactive nitrogen in the soil is going to undergo a microbial reaction at some point depending on the conditions, the temperature, the oxygen in the soil, and the problem is that N2O can be produced in a number of different ways. So really if we have nitrogen in the soil, which is one of our main goals, N2O is going to be an output and it's hard to avoid. The challenge is to try and manage these pathways through different agricultural management practices to allow us to reduce N2O emissions but still maintain high soil and availability that would then be available for crop uptake. If we take a step back and look at, well, why is there a lot of talk of N2O emissions in agriculture these days? What's the big concern? This is a report out by the US EPA. You can find similar data for looking at global N2O emissions. But they said, okay, let's break down all the sources of N2O in the US and look at where they're coming from. And unfortunately, agricultural soil management contributes about 75% of N2O to the atmosphere. Agricultural soil management here, mostly meaning nitrogen fertilizer addition. The problem is that moving forward, if we look to 2030, the IPCC and other scientists estimate about a 30 to 60% increase in these emissions. So even looking at what we have now and how large the concentration has become, we can expect it to go higher before it gets less. So because agriculture represents the bulk of N2O emissions, it's really becoming the target focus for a major opportunity to mitigate these emissions and reduce the impacts of agriculture on climate change. Today, I don't have any results from Illinois that I'm going to be showing you. I'm simply going to introduce you to a few concepts that are out there in the literature. There's been a lot of work on this in the past decade, especially in the past 2 or 3 years. And I'm just going to highlight a few concepts or strategies that can be used to reduce N2O emissions while still maintaining high productivity levels. Before we get into that, again, I just want to highlight the complexity of the nitrogen cycle and also the release pathway of N2O emissions. If we look at the center of our circle here, a very simple representation of fertilizer in, N2O emissions out. Unfortunately, every single phrase or element in this diagram can impact those N2O emissions, and of course there are interactions occurring between all of these different factors. Something on the top here is something that we can manage, nutrient inputs into the field, and here are the 4 R's of nutrient stewardship, source, rate, time, and place. All of those can be managed in certain ways to reduce N2O emissions, as well as cropping system practices, irrigation inputs, rotation, tillage. Those all interact with these soil properties. So although I'm going to be sharing a few results about some of the more common recommendations for how to reduce these emissions, we do have to keep in mind that these pathways change on a day-to-day basis, and predicting emissions over the season and over an entire annual cycle can be pretty difficult. So looking at the literature and really what the focus has been over the years is this relationship right here. We're looking at inputs of nitrogen fertilizer rate and outputs of N2O emission. All the other factors certainly play a role, but if there's one thing that can predict N2O emissions the most, it's fertilizer rate. Now there's some debate on what the shape of the line is and whether this is a straight linear shot up. That's what the IPCC uses, this red line. Other research has now shown that, well, if we're applying relatively low N rates, we can actually have even low N2O emissions down here, but it's only at the really high N rates where we start elevating things exponentially. I think this is an important topic, but many agronomists and soil scientists are starting to move to a different concept of how we can manage N2O emissions, and not just looking at it N rate. Here's another figure. This is a meta-analysis, actually meaning a study of results from other studies. So they just went into the literature, gathered a bunch of data that was available on this topic for corn cropping systems in the Midwestern United States, and pulled together, okay, let's look at the nitrogen rate and for all these systems, as well as N2O emissions, or we can calculate it in a different manner looking at nitrogen surplus. So I'll take a second to describe this metric. This is simply how much nitrogen did we apply relative to how much nitrogen was taken up by the crop. So if you put on 200 units of N, the crop took up 200 units of N. It's a simple measure, but in a nitrogen surplus method, the balance would be 0. So we can see that on this side, yes, as you're increasing N rate, you can draw a blue line, which would be a straight one. You can draw an exponential line, which would be a green one. We see there's a general relationship. The more nitrogen you put in, the higher N2O emissions are going to be. This is, again, what agronomists are starting to focus on more is how can we avoid surplus nitrogen applications. So nitrogen applications beyond those required to meet crop demand and maximum yield. And you can draw a straight line through these. There's not very many significant relationships, but I think it's pretty easy to tell if you're putting in nitrogen rates below a surplus value, N2O emissions remain relatively low, and it's really over on these very high or surplus N values that you get some very high emissions. I would like to point out also, in these systems, there's a lot of dark circles there showing that even in systems with high nitrogen rates, high nitrogen surplus, in these instances, they're actually, the N2O emissions are remaining relatively low. So it is possible to still have low N2O emissions and high N rates. Another management factor that's been looked at extensively, and I would say there's been quite a debate about this over the years, We know no-till practices can influence soil chemical properties, biological properties, the physical structure of the soil. So obviously there's going to be some, over time, there's going to be some impacts on nitrogen cycling as well. So there is the potential for no-till itself, the way it holds soil moisture, the way the nutrients become available to impact N2O emissions. This is another meta-analysis, again, going into the literature and saying, okay, a bunch of people have done studies on this. How can we summarize the effects of all those different studies and come out with some bigger picture understanding of these results? If we look at the effect of no-till and reduced tillage systems on N2O, we see in the short term, that would be no-till systems younger than 10 years, there's no effect. This is a reduction of N2O emissions on this side, an increase on this side, and this is our zero or center line. However, if we look at no-till and reduced tillage systems in the long term, this would be studies more than 10 years, there does seem to be a nice significant reduction. Unfortunately, when you separate these results out and break it down into humid climates versus dry climates, humid being defined as precipitation greater than about 65% of potential evapotranspiration in a season. The Midwest generally, in most years, would qualify as a humid climate. You see that really, no matter if it's a short-term or a long-term no-till system, you're not actually having any significant reductions. Really, where we see the benefits as well as negative impacts of no-till is in dry climates. In the early years in dry climates, no-till can actually increase emissions. In the long term, it can actually reduce emissions. I'm going to talk a minute about the effects of nitrogen source, and theoretically, wouldn't it be nice if our goal was to reduce N2O emissions, we could just switch our nitrogen source to a product that we know reduces them. That would be ignoring a lot of other components of our cropping system and a lot of other decisions we have to make, but at least it would be nice if we could show this product has this impact, so if this is our goal, maybe we could implement it in this amount of acres or so. The problem is the results that are out there have been very conflicting to date. I'll just report on one kind of summary study where a bunch of USDA researchers at multiple sites looked at the effects of enhanced efficiency fertilizers. That's a broad category where they're looking at different products, ESN, Super U, UAN plus Agrotane plus. They're comparing these enhanced efficiency fertilizers to the standard form at a number of different sites across the U.S., Iowa, Kentucky, Colorado, Minnesota, Washington, Pennsylvania. Those are just a few. I think there's actually more. Unfortunately, no sites in Illinois in that study. And unfortunately, they found really very few conclusions that could be extrapolated across these different sites. In some sites, such as Colorado, these enhanced efficiency products worked very well and could reduce N2O emissions by up to 60% without impacting yields at all. The problem was at other sites, I think it was Iowa, that these enhanced efficiency products actually increased emissions. So that's a little counterintuitive. One of the explanations is that if the product is actually keeping a more slow release form, keeping the nitrogen in the soil longer, that's a longer period that it would be susceptible to nitrification, denitrification pathways, and subsequent N2O losses. So these authors conclude that yes, there is some potential, but overall the year-to-year variability in results is really going to be dictated by temperature and precipitation patterns, and it's hard to actually have a firm recommendation at this time. And I'll just conclude with one idea. This is some work that I've been involved with in the past and hoping to start a few projects here in Illinois related to this issue. But several researchers have put forth this idea of, well, instead of just looking at N2O emissions on an area basis, that is units or in this case kilograms of nitrogen dioxide per hectare, why don't we express it as a function of crop productivity? And I'll walk you through that here in a bit. But this blue line, again, is the IPCC. This is the default emission factor, saying if we put in 100 units, 200 units, we're getting 1 unit or 2 units out. It's a 1% linear relationship. But as agronomists, we all know that nitrogen has a very large role in controlling yields each year. This yield curve is maybe a little bit exaggerated, but at low N rates, we see large yield responses. So if we're really thinking about options for meeting global food demand, like Bob mentioned, over the next 35, 40 years, while reducing our environmental impacts, we can't just say, well, let's everybody bring their N rate down to 50 units. I mean, that's not a possibility. So other people have pushed forward this idea of why don't we express our N2O emissions as a function of crop productivity. It's as simple as dividing your blue line by your red line and expressing yield-scaled nitrous oxide emissions. This has gained a lot of momentum in the research community, and also say in the policy-making community. People are no longer just talking about reducing emissions, they're talking about reducing emissions intensity. That just means emissions per unit yield. This figure is one nice example of this. This is, again, a meta-analysis taking data from other papers. On the y-axis, we have yield-scaled nitrous oxide emissions. On the x-axis, again, we have this idea of nitrogen surplus. That's nitrogen applied minus nitrogen taken up by the crop. And the conclusion here is that if you have deficit nitrogen rates or going up to nitrogen rates that meet crop demand, you're actually getting no significant increase in yield-scaled emissions. You're only getting this large increase in yield-scaled emissions when you're having nitrogen rates that are far beyond that of crop demand. So if you're trying to manage agricultural systems in a way we're getting very high productivity with a minimum amount of emissions per unit productivity, really the conclusion is to manage your N rates in a way that you're getting optimum yields and nitrogen uptake. So I think some short conclusions here. Yes, on the one hand, we can say that N2O emissions are inevitable. They're always occurring in agricultural systems. But I think there is also an opportunity here for agriculture to realize that it can play a large role in reducing them. To the extent possible, Emerson's going to talk a lot more about this, but managing nitrogen rates to meet crop demand in a given year would be one promising opportunity. This is largely meaning just avoid excessive nitrogen rates that are beyond that of crop demand. And while recognizing that results are variable, we can be aware of management practices that are out there, and there's some research results to support that can help reduce N2O emissions without impacting agronomic outcomes. And with that, I'll hand it over to Emerson and Dan.